Welcome back to the video lecture series for Introduction to Additive Programming using Scala. So we've looked at a number of different uses of regular expressions, and I want to come back and talk about the grammar demo that appeared earlier in this chapter. So we had this little program, and if I run it, you will probably remember what this looked like, and this gave us the ability to input grammars. And we did something like, actually, the last one that we did was an AC, and then A goes to AAB, or it goes to AB, and C goes to either C or CC, and parse and advance. Since making that video, I have actually written a little bit of extra code so that it doesn't put a whole bunch of duplicates in here. But I want to show this code because this code happens to make very nice usage of regular expressions. And so if we pull that off to the side. So here is the code that was used to make that. And we start off just setting up simple GUI. That's not too significant to us. But inside of this GUI there's basically these three buttons that we have, the parse, advance, and reset, and so I have some methods to do those. The parse is where I use my regular expression. So when I type in this A arrow and then what A can become, I match this with a regular expression that has, so notice the grouping parentheses, and then anything that is a letter. So I didn't put a \W, which would have been for a word character, because word characters always also include digits, and I really didn't want to allow digits in here because I want the lowercase letters to be terminals and the uppercase to be non-terminals. Hey, look at that. There's actually a typo in there. Not that it didn't impact the processing as long as I typed things in properly, but that probably would have actually accepted numbers because of that typo. And then the plus saying that there can be one or more of these. Now for the regular and context-free grammars, there can really only be one, and I could remove the plus, but this allows it to parse out more general rules. And then there can be one or more spaces. You might notice that in here I did space out my between the character and the arrow, and I have another space over here. I don't have to have those, and I could have multiple of them. And since the user is typing these things in, it's nice if we don't restrict the user and what they can type in. So I put a \/s plus, which will match one or more white spaces. In fact, if we want to make it so they don't have to type in any, we could change those to stars instead. In fact, I should go ahead and kill the program at this point because we've made some interesting changes. And then on the other side, I have a combination of lowercase letters, uppercase letters, spaces, and ors, and one or more of those on the other side of the production. So if we run this, it will do, for our purposes, what it did before. S goes to A or a S was a simple regular one that generates one or more S's. And because of how we've changed this now, theoretically I could take out all the white spaces from this and parse it, reset, advance, and it still works. Okay, so the advantage of using a regular expression here is just if I had done something other than a regular expression to pull apart these sides, this would have been more challenging. Down in here, so I take the productions area, I take the text out of it, I trim it, and then I split it up on new lines because each line in there is going to be one of these productions. Then I create my rule set by going a for loop over all of these rule strings where I match it on this pattern. So the first group here is the stuff before the arrow, the second group here is the stuff after the arrow, so I pull out start and options there. And then I return a tuple that is the first character of start, along with all of those options split on the pipe. Note, because split takes a regular expression, I have to backslash my pipe here, because pipe means something special in regular expressions. And then I trim off any white spaces around those things and convert it to a list, because the way I'm storing my grammar is as a map from char to list of string. And then I can take this result and simply convert it to a map, and that gives me that those productions, that map of char to list of strings. And it's fairly simple to do my advance. Then I run through, though one thing that's interesting to note about this, I am using a fairly complex for comprehension here that has a generator that goes through all of the elements of my current list. So to start off with, that was just S. If we start this back off, the current list is just that, and when I advance it, it changes to this. You've seen from other examples this list can get longer, and so this is running through every one of those. For each one of those strings, I want to run through every character location in there, and then if that character is uppercase, I look up the production in it, and I run through all of the options in the productions, because remember, the productions is a map from a char to a list of strings, so this will run through each result in that list. And then I use the patch function to replace the one character that had been at location I with the result from the other side, and this winds up building a whole new set of strings for us, and that is all the possible results, both the ones that are completely terminal and the ones that include non-terminals. So I partition those out. If the string contains something that is uppercase, so if there exists in the string a character that is uppercase, it sticks it in the current side, otherwise it says that it's one of the things that are done. And the change that I made since the previous video was I added these two calls to distinct so that we don't get duplicates in there. So this, I think, is a very nice little example of how we can use regular expressions in a number of places to help simplify a programming problem where we have to do a fair bit of string manipulation, and we can add a lot of flexibility to it by putting in the appropriate regular expression.